Today we're going to continue referencing our German tank activity and the things we talked about yesterday, as well as get into really what a sampling distribution is. But first we need to talk about something called sampling variability. Okay, sampling variability is the fact that the value of a statistic varies with repeated sampling. And if you think about it, this makes a lot of sense, because whenever we draw samples, we're not going to get the same numbers every time because they're random samples. So when I calculate a statistic based on my random sample, it's probably not going to be the same every time. So it's going to vary. If you think back to the German tank problem, when we were drawing samples and calculating our estimated maximums, we weren't getting the same thing every time. That's because our samples were different. That's sampling variability. So let's look at an example, and we'll see a little bit of sampling variability here, as well as introduce sampling distributions. I have a distribution here, and this is my population, and it's 200 chips, 100 red and 100 blue. And you'll see that I'll graph the distribution, which this is also a good time for us to remember that a distribution, the definition, is simply the descriptions of what values a variable can take and how often it takes those values. So here my variable can take the values blue and red, and it takes each of those 50% of the time, making this a uniform distribution. Okay, so let's delete that. And let's get a sample of chips here, and if I take a sample, I'm going to select sample 20 cases. Okay, and if I look at my 20 cases, I will see that some of them are red and some of them are blue. And what if I was actually interested in the proportion that were red? So I'm going to go over here and I'm going to create a sample statistic called proportion red. This would be p hat. And in my formula, I'm going to say I want to know the proportion that are the color red. And here it's 0.4. Okay? If I were to take another sample, I probably wouldn't get the same thing, so I might have a different proportion. So what we're going to do then is we're going to go back up here and we're actually going to do that. We are going to take a lot of samples. That's what's going on here. It just took 5 samples. Instead of 5, we're actually going to tell it to take 100. Okay, and each time it's going to take a sample. This is what it's doing. It's taking a sample and it's finding the proportion of them that are red. And then I can graph this, and we can look at it in table form, and you can see that every one of them are different. So if I graph it, that'll help me easily to see my distribution. We can go ahead and move this out of the way so we have more room. We can see our distribution of chips that were red. And we see that we have a unimodal distribution. It's fairly symmetric. It has a center of around 0.45, 0.5, maybe even somewhere around in there. And as far as spread goes, I can say easily that I see that it has a range from 0.25 to 0.75, which is about 5. Okay, remember that whenever you discuss a distribution, you always want to talk about the shape, the center, the spread, and any outliers, which I don't see any outliers here. Okay, what we have here is, imagine that each of these dots is a p hat. Okay, I have taken 100 samples, and each of those samples found the proportion in the sample that are red and graphed each of those proportions here. There are 100 of them. There are actually many more samples that we could take. Okay, there are more samples that you can take of 200 chips of size 20 than we could possibly ever take. We would never figure them all out. Okay, this is what we call the beginnings of a sampling distribution. A sampling distribution is where you take all possible samples of the same size so in this case size 20, all possible ones, and I find the proportion or whatever other statistic I'm looking for each one, and then I make a distribution of those statistics. Okay, the actual definition is that it is the distribution of values taken by the statistic in all possible samples of the same size from the same population. This diagram here gives a perfect example of that. Here we have our population distribution of our 200 chips. Okay, this is a distribution. It's a distribution that shows us what values the population can take. Okay, so it's this distribution right here, distribution of the population. Each of these is a distribution of a sample. So if I take a sample of 20, it might look like this. It might look like this. It might look like this. It might look like something totally different. All of those are distributions of samples. And then this is the sampling distribution of a sample statistic. Okay? It is if I took all the possible samples, found the p-hats for each one, and then graphed them all, this is what that graph would look like. Okay, it's important to notice that here we have 3 different types of distributions. With 3 different types of distributions, I always want to make sure that I'm being very specific about which one I am talking about. I cannot just say the distribution. I must say the population distribution, or the distribution of the sample data, or the sampling distribution. Also, let's look at this. Notice that what we did earlier here is not a sampling distribution because I do not have all the possible samples. I have the great beginnings to one, but not a sampling distribution. Also notice here that I can use this, even though it's not a sampling distribution, to tell me something about the population. Okay, we know that the population is half red, half blue. But if I didn't know that, let's say that I did not know that, and my teacher told me that it was 70% red. I would look at this and say, I doubt that's true because very few of our samples actually had a proportion that was 70% or higher. It would be way more likely for my true proportion to be somewhere in here, okay, where the majority of my data is. That is what's so useful about sampling distributions. They give us what we call unbiased estimators. An unbiased estimator is a statistic, well, a statistic is an unbiased estimator. If the mean of its sampling distribution is equal to the true value of the parameter. Okay? Oftentimes we will never create our own sampling distribution. It's just too time consuming and there's too many variables. But we can take rules that other people have given us from sampling distributions that they have created to know that this is true. Certain statistics are unbiased estimators and some are not, and we will discover those as we keep going. But unbiased estimators are great for helping us to make predictions about populations. That doesn't mean that they are perfect. It will not give us the exact value every time. What it does mean, though, is that estimations that we get from the statistics that are unbiased, even from individual samples, are going to be close and consistent to the actual parameter. So much like in this sampling distribution up here, we know that it was half and half. So our mean here is at 0.5. And while we have a few that are far out, most of ours are close and consistent to 0.5. Okay, I can reduce this variability by increasing my sample size. So if I go back to this, and we looked at this as being our 30 chips, I'm actually going to change the name here so that I know that this is a sample of 30. And I'm going to create some more samples that are a different size, a larger size, so we can see what happens. Instead of 30, I'm going to make it 40. And let's collect these. I still need them to measure the proportion that are red. It's going to give me a proportion that are red. And then I'm going to come over here and I'm going to collect 100 of those, just like we did earlier. Okay, I'm going to name this so that I know that this sample size is 40. And then there's my table from my sample of 40. We're going to graph it so that we can see it in comparison to this one. And you'll notice that if I line my graphs up so that my scales look pretty similar, you will notice that I have a smaller range. Just by increasing the sample size by 10, I reduced my range from 5 to 4. Okay, the larger we make our sample sizes, the less variability there is in the sampling distribution. It's very important to note that we're only talking about the sampling distribution. In regular distributions, that's not the case, but in sampling distributions, increasing your sample size reduces variability, assuming that you used a correct sampling process to begin with. If you're using a convenience sample, there's nothing that's going to help you. So if I go back to this, notice that's one way I can reduce it, is by increasing the sample size. The population size does not actually have an effect on the variability of the statistic. Okay, as long as the population is at least 10 times the size of our sample. Okay, our earlier example wasn't, but in all of our other cases, as long as our population is 10 times the size of our sample, then the size of the population does not affect the variability. Notice these two graphs, that this one is much more variable than this one. Okay, they came from the same population, they both are 1,000 samples, but this sample size was 100 and this sample size was 1,000. That's why this one is much less variable than this one. So key points: definition of a sampling distribution, increasing sample size reduces variability, and being able to begin a sampling distribution, even if we can't totally complete it.